The data provided in the steam tables can also be expressed in a graphical form. The following figure illustrates the relationship between the enthalpy and temperature of the various states of water and steam. This is known as a phase diagram. The blue region corresponds to sub-saturated water. The red region corresponds to superheated steam. The region in the middle, in the form of a dome, corresponds to wet steam, where the two phases, liquid and gas, so water and steam, coexist. The solid line on the left side of the dome represents saturated water. Any point on this line will have a dryness fraction equal to 0. The solid line on the right side of the dome represents dry, saturated steam. Any point on this line will have a dryness fraction equal to 1. Now, as water is heated from point A, 0 degrees Celsius, to its saturation temperature at point B, its condition follows the saturated water line until it has received all of its liquid enthalpy, as depicted here. If further heat continues to be added, the water changes phase to a water-vapor mixture and continues to increase in enthalpy while remaining at saturation temperature. As the water-vapor mixture increases in dryness, its condition moves from the saturated liquid line to the saturated vapor line. Therefore, at a point exactly halfway between these two states, the dryness fraction is 0.5, as seen here. In a similar manner, on the saturated steam line, the steam is 100% dry, so the dryness fraction is 1. Once it has received all of its enthalpy of evaporation, it reaches the saturated steam line at point C. If it continues to be heated after this point, the pressure remains constant, but the temperature of the steam will begin to rise as superheat is imparted, as depicted here. The degrees of superheat in this example can be determined graphically as follows. The saturated water and saturated steam lines enclose a region in which a water-vapor mixture exists. This mixture is referred to as wet steam. In the region to the left of the saturated water line, only water exists, and in the region to the right of the saturated steam line, only superheated steam exists. The point at which the saturated water and saturated steam lines meet is known as the critical point. As the pressure increases towards the critical point, the enthalpy of evaporation decreases until it becomes 0 at the critical point. This means that water changes directly into saturated steam at the critical point. The critical point is the highest temperature at which water can exist. Any compression at constant temperature above the critical point will not produce a phase change. Compression at constant temperature below the critical point, however, will result in liquefaction of the vapor as it passes from the superheated region into the wet steam region. The critical point occurs at 374.15 degrees Celsius and 221.2 bar absolute for steam. Above this pressure, the steam is termed supercritical, and no well-defined boiling point applies. The term flash steam is traditionally used to describe steam issuing from condensate receiver vents and open-ended condensate discharge lines from steam traps. But the question is, how can steam be formed from water without adding heat? Actually, flash steam occurs whenever water at high pressure and a temperature higher than the saturation temperature of the low pressure liquid is allowed to drop to a lower pressure. Conversely, if the temperature of the high pressure water is lower than the saturation temperature at the lower pressure, then flash steam cannot be formed. In the case of condensate passing through a steam trap, as in this example, it is usually the case that the upstream temperature is high enough to form flash steam. In this configuration, consider a kilogram of condensate at 5 bar gauge and a saturation temperature of 159 degrees Celsius passing through a steam trap to a lower pressure of 0 bar gauge. According to the steam tables, the amount of energy in 1 kilogram of condensate at saturation temperature at 5 bar gauge is 671 kilojoule. In accordance with the first law of thermodynamics, the amount of energy contained in the fluid on the low pressure side of the steam trap must equal that on the high pressure side, and this constitutes the principle of conservation of energy. Consequently, the heat contained in 1 kilogram of low pressure fluid is also 671 kilojoule. However, water at 0 bar gauge is only able to contain 419 kilojoule of heat, as it was discussed in a previous video. Subsequently, there appears to be an imbalance of heat on the low pressure side. This imbalance is equal to 671 kilojoule minus 419 kilojoule, that is 252 kilojoule, which in terms of the water could be considered as excess heat. It is this excess heat that boils some of the condensate into what is known as flash steam, and the boiling process is called flashing. Therefore, the 1 kilogram of condensate, which existed as 1 kilogram of liquid water on the high pressure side of the steam trap, now partly exists as both water and steam on the low pressure side. The amount of flash steam produced at the final pressure can be determined using the following simple equation. It is equal to the difference of enthalpy of steam at both pressures, P1 and P2, divided by the enthalpy of evaporation at the final pressure. Now, in our previous example, the difference of 252 kilojoule per kilogram of heat energy would then produce flash steam at atmospheric pressure. Therefore, using the equation, the flash steam produced would be as follows. So, 0.112 kilogram of steam per kilogram of water, or simply 11.2% by weight. The proportion of flash steam produced can be thought of as the ratio of the excess energy to the enthalpy of evaporation at the final pressure. Okay, let's now consider the case where the high pressure condensate temperature is lower than the low pressure saturation temperature. So consider the same conditions as in the previous example, with the exception that the high pressure condensate temperature is no longer 159 degrees Celsius, but only 90 degrees Celsius, as seen here. This means that the liquid or the condensate at the inlet of the steam trap is subcooled. In this case, the sub-saturated water table will show that the liquid enthalpy of 1 kg of condensate at 5 bar gauge and 90 degrees Celsius is 377 kJ. As this enthalpy is less than the enthalpy of 1 kg of saturated water at atmospheric pressure, then there is no excess heat available to produce flash steam. Therefore, the condensate simply passes through the steam trap and remains in a liquid state at the same temperature, but lower pressure, atmospheric pressure in this case. The principles of the conservation of energy and mass allow the flash steam phenomenon to be thought of from a different direction. Consider the conditions in the previous example. We have seen that 1 kg of condensate at 5 bar gauge and 159 degrees Celsius produces 0.112 kg of flash steam at atmospheric pressure. This can be illustrated schematically in the next figure as seen here. The total mass of flash and condensate remains at 1 kg. The principle of energy conservation states that the total energy in the lower pressure state must equal the total energy in the higher pressure state. Therefore, the amount of heat in the flash steam and condensate must equal that in the initial condensate, 671 kJ. The steam tables gives the following information. The total enthalpy of saturated water at atmospheric pressure is 419 kJ per kilogram, and the total enthalpy in saturated steam at atmospheric pressure is 2675 kJ per kilogram. Therefore, at the lower pressure state of 0 bar gauge, the total enthalpy in the water equals the mass of the water times the total enthalpy of saturated water, so 0.888 kg times 419 kJ per kilogram. This gives 372 kJ. The total enthalpy in the flash steam is equal to the mass of flash steam times the total enthalpy in saturated steam, so 0.112 kg times 2675 kJ per kilogram. That is 299 kJ. The total enthalpy in condensate and flash steam at the lower pressure of 0 bar gauge is therefore the sum of the two enthalpies, so 372 plus 299, that is 671 kJ. Therefore, according to the steam tables, the enthalpy expected in the lower pressure state is the same as that in the higher pressure state, thus proving the principle of conservation of energy.